Welcome to this video. This video is a short video to give a non-technical introduction to one of the main mathematical philosophies which was widespread during the first half of the 20th century. At the time, there was much philosophical discussion regarding the foundations of mathematics following the discovery of certain paradoxes and contradictions which seem to have crept into mathematics and which threatened to undermine the certainty of the results that mathematics prided itself on. The main schools of thought were Logicism, Formalism and Intuitionism, though these names may not have been used at the time and may have been applied retrospectively. Of course, there were other philosophies and narrower schools of thought within these schools of thought, but these three are recognised as the three main philosophies which were prominent at the time. Each school of thought was battling it out for supremacy, claiming that they held the key to the true foundational principles of mathematics. This video will, therefore, focus on the first of these, Logicism. I don't intend to give a comprehensive treatment of Logicism here. In such a short video as this, it's clear that many details will have to be omitted. I simply want to give some idea of the Logicist Thesis and some historical context. I'll touch on some of the criticisms of Logicism, but I won't be going into too much detail on any aspects really throughout this video. Throughout the video, I'll often be relying on a number of quotes taken from various authors who possibly were more directly involved with Logicism, or at least were around at the time that Logicism was at its height. I won't be making any real attempts to determine whether Logicism is or was correct as a philosophy. Logic has, of course, played a part in arithmetical and geometrical reasoning for centuries. You only have to look through Euclid's Elements to see principles being used that we would recognise today as basic logical principles. However, logic was only really used as a tool to aid in arithmetical and geometrical reasoning insofar as these types of reasoning were considered a form of rational thought. Logic simply gave the rules by which rational thought could proceed correctly. The Logicist Thesis is that all of classical mathematics, as it stood at the end of the 19th century and start of the 20th century, can be reduced to a handful of elementary and clearly logical principles which are indubitably self-evident. So that is, that effectively, mathematics can be considered as nothing more than a branch of logic. Thus, logic was to be put centre stage in the spotlight and shown to be the big brother of mathematics. A logicist refers to someone who largely subscribes to the Logicist Thesis, and Logicism is the mathematical philosophy largely held by a logicist. Let's have a look at how various authors have described the aims of the logicists and the Logicist Thesis. In Philosophy of Mathematics, 2nd edition by Benacerraf and Putnam, we have that Logicism arose out of a concern with the nature of mathematical truth, and logicists hoped to show, as against Kant, that mathematics did not have any subject matter, but dealt with pure relations among concepts, and that these relations were analytic, that is, of the same character as the principle of non-contradiction or the rule of modus ponens. Stephan Korner, in his book Philosophy of Mathematics, says, "The logic to which logicism holds pure mathematics to be reducible presupposes the fundamental dichotomy of all knowledge into empirical and non-empirical, or, as it has become customary to express it since the time of Kant, into a posteriori and a priori." Korner goes on to say that in its original form, logicism assumed that there is a hereditary characteristic L of logical propositions, namely their logical character, and it set out to show that 1. Certain propositions, say L1 to Ln, do among others obviously possess L, and 2. From these, all the propositions of pure mathematics, among them, say M1 to Mn, can be formally deduced. The propositions of pure mathematics, therefore, also possess L. This is suggesting that if L is truth, then truth is a hereditary characteristic of the propositions of pure mathematics, in the same way that truth is a hereditary characteristic of the propositions of logic. In the article The Logicist Foundations of Mathematics, Rudolf Carnap says, "We will split the Logicist Thesis into two parts for separate discussion. 1. The concepts of mathematics can be derived from logical concepts through explicit definitions, and 2. The theorems of mathematics can be derived from logical axioms through purely logical deduction." And after introducing various logical concepts such as, amongst others, negation of a sentence, disjunction of two sentences, conjunction and implication, Carnap says, "It is the logicist thesis, then, that the logical concepts just given suffice to define all mathematical concepts, that over and above them, no specifically mathematical concepts are required for the construction of mathematics." And the second thesis can be restated thus: "Every provable mathematical sentence is translatable into a sentence which contains only primitive logical symbols and which is provable in logic." And finally, in The Nature of Mathematics by Max Black, he says, In the Logicist Thesis, the problem of adequately symbolising mathematical expressions reduces in general to the problem of analysing the interconnections between propositional functions and descriptions. Great care is taken by the logicist in the demonstrations of the propositions of logic and mathematics to ensure that, as best they can and with varying degrees of success, that each step of a demonstration proceeds using purely logical principles, and that no extra logical principles are inserted into the demonstrations. Leibniz was, seemingly, amongst the first to really conceive of a universal science based on mathematics, and he's sometimes credited as being the one who really set the ball rolling with what would eventually become the logicist movement. In The Philosophy of Mathematics by Korner, he says, nonetheless he, that's Leibniz, anticipated modern movements, in particular modern logicism, by bringing logic and mathematics together. In the mid-19th century, George Boole made a significant step in logic through his mathematisation of logic in his 1847 book, The Mathematical Analysis of Logic. Boole has played a major role in the uniting of mathematics and logic, with Boolean algebras playing an essential role in contemporary logic, but it was never his intention to subordinate one to the other. Nonetheless, his work contributed to the direction in which mathematics and logic would be taken over the coming decades. Frege took the next big step with his attempt to develop a symbolic language to express mathematical propositions and carry out deductions in his 1879 work, which evidently roughly translates into English as concept writing or concept notation. Unfortunately, Frege's symbolic language was quite cumbersome and didn't really catch on, but his ideas of logicising mathematics would eventually shine through. His later 1884 work, whose title in English is The Foundations of Arithmetic, would present his ideas of a logical formulation of the concept of number. Since much of mathematics had been arithmetised through the works of Dedekind and Weierstrass, amongst others, then it was becoming clear that if a satisfactory logical formulation of the concept of natural number could be developed, then it may be possible for all of mathematics to be logicised. Stephan Korner says, the period which begins with them, that's Boole, Frege and Peirce, has for its most characteristic feature recognition of the close relationship between the two fields, mathematics and logic, which too, strangely enough, had hitherto developed quite separately. Peano also developed a symbolic language in which to express mathematical propositions in his 1895 book, whose title in English is Formulation of Mathematics. This symbolic language was much more convenient to use than Frege's symbolic language, but it was still very prototypical. By way of contrast, Frege's work seems to be concerned with the definition of mathematical concepts in terms of logical concepts, which is the first part of the Logicist Thesis in Rudolf Carnap's comment earlier in the video. And Peano seems to have been more interested in expressing mathematical propositions in terms of logical propositions, the second part of the Logicist Thesis in Carnap's division. Neither the works of Frege nor Peano had any real immediate impact. Their ideas went largely unnoticed except for a certain British philosopher and mathematician called Bertrand Russell. After discovering the works of Frege and Peano, Russell saw huge potential in Frege's ideas and Peano's symbolic notation. In 1903, Russell published his work Principles of Mathematics, and it's immediately clear what his thoughts are regarding the relationship between logic and mathematics. For example, in the preface to the Principles, he says, the present work has two main objects. One of these, the proof that all pure mathematics deals exclusively with concepts definable in terms of a very small number of fundamental logical concepts, and that all its propositions are deducible from a very small number of fundamental logical principles, is undertaken in parts 2 to 7 of this volume, and will be established by strict symbolic reasoning in Volume 2. The Volume 2 that he refers to is what would eventually be published as an independent work titled Principia Mathematica. And he continues, the other object of this work, which occupies part 1, is the explanation of the fundamental concepts which mathematics accepts as indefinable. The first line of the first section of the Principles, titled The Definition of Pure Mathematics, reads as follows. Pure mathematics is the class of all propositions of the form P implies Q, where P and Q are propositions containing one or more variables, the same in the two propositions, and neither P nor Q contains any constants except logical constants. Leaving us in no doubt as to what Russell thought about mathematics being nothing but a part of logic. Admittedly, he did change his mind on his definition of pure mathematics by the time of the second edition of the Principles, but only to accept that there may be other forms of propositions with which pure mathematics may be concerned. He says in the introduction to the second edition of the Principles that the form P implies Q is only one of the many logical forms that mathematical propositions may take. So this doesn't mean that he had abandoned his ideas that mathematics could be reduced to logic, but that he had had to slightly update his thinking. In the Principles, Russell lays out his ideas in a rudimentary form. He introduces the primitive terms and shows how he imagines mathematics being derived from logic. He He covers classes, relations, cardinal numbers, ordinal numbers, and many others. He develops the theory of classes from the logical principles and then, in paragraph 111 of the Principles, goes on to define the cardinal number of class as the class of all classes similar to a given class. As is well known though, just before the Principles was published, Russell discovered the famous paradox which arises when we attempt to consider the class of classes, which are not members of themselves. This contradiction is presented in chapter 10 of the Principles, and Appendix B gives a very brief outline of the solution, the doctrine of types. The most famous work coming from the Logicist school of thought, and which naturally deserves considerable attention when discussing Logicism, is without a doubt Principia Mathematica. Co-written by Alfred North Whitehead and Bertrand Russell, this was originally intended to be a sequel to the earlier Principles, but became such a huge project that it became a completely separate work. In this monumental work, Whitehead and Russell managed to resolve some of the problems that Russell had encountered following the publication of the Principles. In particular, the problem arising from Russell's paradox. The doctrine of types, introduced as a short appendix in the Principles, was expanded upon, leading to a 3-volume work of around 1,900 pages, published between 1910 and 1913. This marks the golden age of Logicism, the time when Logicism was showing the most promise. Both the significance and the aim of Principia Mathematica are often misunderstood and or misrepresented, usually by those who possibly haven't bothered to read any part of it in any detail. Often Principia Mathematica is described as something like a book which takes about 1,000 pages to prove that 1 + 1 = 2, as if this was the sole aim of Principia Mathematica, and as if the authors had nothing better to do. I personally find comments such as this to give a hideous misrepresentation of the scope and seriousness of Principia Mathematica, and comments like this almost present the work as a kind of joke. Principia Mathematica was intended to be the first step in Whitehead and Russell's overall aim to reduce all of human knowledge to logical principles. This was certainly no joke. The reduction of mathematics was merely the first part of that. It's true that around 1,000 pages into the book, it's proved that 1 + 1 = 2. If, however, this had been the only or main aim of the work, it could have been done in a much shorter space. It's a minor result in Principia Mathematica, and it's not by any means the reason for Principia Mathematica being written. Principia Mathematica gives a series of primitive ideas and primitive propositions, some of which are shown on the screen now, and proceeds to derive large portions of mathematics using the theory of types. A detailed exposition of the theory of types will not be given here, though you can see some of the other videos on my channel which go through, in some detail, some of the contents of Volume 1 of Principia Mathematica. I plan to make more videos in the future to add to the ones already there at the time of recording this video. Sadly though, it was all downhill from here for Logicism. Whitehead and Russell made a colossal attempt at driving through the Logicist programme. However, Principia's success was matched only by its failure, praised by many but also heavily criticised. According to some critics, Whitehead and Russell had resorted to using non-logical principles. The main culprit was the so-called axiom of reducibility, though the axiom of infinity came in for some criticism as well. This complicated axiom, which I have a video on my channel explaining, seems to be anything but obvious or self-evident. Indeed, the axiom of reducibility lacks self-evidence to such an extent that Whitehead and Russell felt the need to include a short section in the introduction to Principia Mathematica, explaining why the axiom should be accepted. The authors state in the introduction to the first edition that the axiom of reducibility is self-evident is a proposition which can hardly be maintained. But in fact, self-evidence is never more than a part of the reason for accepting an axiom, and is never indispensable. Do we possibly see here, then, that the logicist dream had already failed? Do we see that the authors knew that they had already deviated from their original aim, but were reluctant to openly admit it? Stephan Korner in the Philosophy of Mathematics says, "The programme of Logicism is to deduce mathematics from logical principles, not from principles some of which are logical and some not." Frank Ramsey appears to have largely been supportive of Logicism, but was critical of the system outlined in Principia Mathematica. In his 1925 paper, The Foundations of Mathematics, he says, "I hold that mathematics is part of logic, and so belongs to what may be called the logical school, as opposed to the formalist and intuitionist schools." Ramsey makes an attempt at updating the system of Principia Mathematica by incorporating some of the ideas of Wittgenstein, and also says, regarding the axiom of reducibility, that such an axiom, the axiom of reducibility, has no place in mathematics, and anything which cannot be proved without using it cannot be regarded as proved at all. From the moment of its publication, Principia Mathematica's weaknesses were ruthlessly exposed. A second edition published a decade or so later in the mid-1920s tried to correct some of the problems of the first edition. But developments elsewhere were moving too quickly, and the Principia juggernaut just simply couldn't keep up. Ultimately, Principia Mathematica quickly became redundant and largely irrelevant. The notation became unwieldy, and it seemed that axioms had to be introduced on a rather ad hoc basis to deal with the various difficulties that arose, something that Imre Lakatos refers to as monster barring. Not only that, there was always the fly in the ointment, which was the potentially non-logical principle, the axiom of reducibility. It became clearer as time went on that the project had failed in its original aim. Speaking of the system of Principia Mathematica, Imre Lakatos says in his article Foundations of Mathematics that the intended logico-trivialization of mathematics degenerated into a sophisticated system including axioms like that of reducibility, infinity, choice, and also ramified type theory, one of the most complicated conceptual labyrinths a human mind ever invented. Nonetheless, the impact of Principia Mathematica can't be underestimated. It fell short of its goal, but it revolutionized logic and mathematics in many ways. Principia Mathematica has inspired the development of numerous formal symbolic languages over the decades since its publication. The Logicist movement received its final blow in the early 1930s from Gödel with his quoted-to-death incompleteness theorems, which showed that the formal system of Principia Mathematica was doomed to failure from the outset. It was recognised that, although indeed parts of mathematics can be formulated in logical terms, there is something which separates mathematics from logic, some mathematical principles which cannot be adequately captured by logic alone. Hermann Weyl was critical of the system of Principia Mathematica, and though he wasn't against the idea of reducing certain aspects of mathematics to logic, he says in his 1918 book The Continuum, the principle of iteration, by far the most complex of all, is the specifically mathematical one. Presumably from this, we're to understand that Weyl believes that the principle of iteration cannot be reduced to purely logical principles, since if it could, then it would not be a specifically mathematical principle. And he goes on to say, it has become more common of late to regard the distinction between mathematics and formal logic as problematic. But in our view, it's obvious that, however closely related the two may be, mathematics stands apart from logic as a science whose distinctiveness is clearly marked. Weyl eventually gave up on Logicism and joined L.E.J. Brouwer in the Intuitionist movement. Thus the Logicist movement fizzled out. There were some, such as Quine, who continued to formulate parts of mathematics in logical terms, making improvements on the system of Principia Mathematica through his own system, mathematical logic, abbreviated to ML, in 1955, but the movement had largely lost its momentum. Mathematically minded philosophers and philosophically minded mathematicians had moved on. Even Bertrand Russell, the poster boy of Logicism, had long since lost interest in mathematics and logic and had moved on to philosophizing about other things. In the philosophy of mathematics, Stephan Korner says, he, that's Quine, claims that the notion of arithmetic can be defined in purely logical terms. And he goes on further to say of Quine, he doesn't claim to have deduced the theorems of arithmetic from purely logical principles. In the introduction of Philosophy of Mathematics by Benacerraf and Putnam it reads, logicists did not reduce all of mathematics to elementary logic, but they did reduce mathematics to elementary logic plus the theory of properties, or sets, properties of properties and so on. Thus if property theory, or set theory, may be counted as part of logic, mathematics is reducible to logic. The uniting of mathematics with logic is, then, a relatively recent development occurring only within the last century and a half or so. And although the aim of the original logicist school has been shown to be untenable, and the aims of anyone who may call themselves a logicist will necessarily have to be more modest aims than those of Russell, Whitehead and Frege, it can't be denied that the investigations into what extent elementary logic can provide a foundational basis for mathematics have had a profound impact on the direction of mathematics, even if that impact is not fully recognised and appreciated by everyone today. It's been shown through the investigations of the logicist that symbolic and formal languages can be used to great effect in deductive reasoning, though of course there are some very definite limitations to using such languages. I can't imagine that anything more than a handful of modern mathematicians will have any familiarity with, or indeed any interest in, Principia Mathematica beyond the title. The fact is that the works of Frege, Russell and Whitehead and so on are not directly relevant to modern mathematics. No one would dream of using Russell and Whitehead's system. However, logic is almost taken for granted in contemporary mathematics, and although working mathematicians may not need to be experts in logic, it's generally accepted that there is a close relationship between logic and mathematics, and that logical principles often underlie and can be used to justify much of what a mathematician does, even if those principles are not at the fore. But mathematics is distinct from logic. Mathematics now, as it has for centuries, proceeds along mostly fairly intuitive lines. Mathematicians typically do not prove things using formal logic. Mathematicians will naturally feel what is acceptable and valid, and what is not, without a direct appeal to formal logic. It's not of any real concern to modern working mathematicians whether what they do can be explained by logical principles. I certainly don't disagree with this attitude. Mathematicians are interested in doing mathematics, and they are the ones who decide what is and is not mathematics. Nevertheless, in their book Philosophy of Mathematics, Benacerraf and Putnam say, "It should not be forgotten that if today it seems somewhat arbitrary where one draws the line between logic and mathematics, this is itself a victory for Frege, Russell and Whitehead. Before their work, the gulf between the two subjects seemed absolute." Were it not for works such as Frege's Foundations of Arithmetic and Whitehead and Russell's Principia Mathematica, then the development of the highly sophisticated formal languages used in modern logic and mathematics would have probably occurred much later, though I doubt very much that they wouldn't have occurred at all. It was recently brought to my attention by a commenter of one of my other videos that there are still some individuals who subscribe to a range of views roughly described as neo-logicism. It seems then that logicism is not completely dead and still exists in one form or another, though I doubt with exactly the same aims as during the time of Frege and Russell. Thank you for watching this video. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know, and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.